A line or a plane that is perpendicular to a segment at its what? Midpoint. All right. Equidistant. Have you ever heard of that word before?
Yes, from yesterday, yeah.
Oh, that's right. That's right. Equidistant is a point that is the same distance from two figures or two points or something like that. We're going to look at that today. Concurrent. I don't know if there is one. When three or more lines, rays, or segments intersect in the same point. That means they're concurrent. Okay? So then, as I was typing these yesterday, I'm like, point of concurrency? Really? What do you think point of concurrency is? I'm like, do I really need to define that? Right, it's the point where the concurrent lines intersect. Right? Like, I'm not going to type that. All right. Circumcenter of a triangle. Circumcenter. It has something to do with a circle, but it also has to do with a triangle. So it's the point of concurrency of three perpendicular bisectors of a triangle. So if you take the perpendicular bisector of every side of a triangle, it's where those perpendicular bisectors intersect. It's called the point of concurrency, and it's also the circumcenter of the triangle. So we'll see that on the other side. All right, perpendicular bisector theorem. So in a plane, I'm going to draw a picture here so don't get too over enthusiastic and turn over. In a plane, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So I'm going to just kind of clarify this a little bit. Here's a segment. Draw a segment. And then I'm going to draw the perpendicular bisector of that segment. So I'm just going to make a right angle there. Not only is it a right angle, but it does what here? It's the midpoint, right? Cuts these in half. Okay, now this is saying, this theorem, if I take a point anywhere on this perpendicular bisector and I connect it to the endpoints of the segment, it's saying that those are congruent. So there's that one point. There's another point up here. If that sits on that perpendicular bisector and I connect it to the endpoints, that's congruent to that. Equidistant. Equidistance. The same distance. Likewise, if I picked a point like way down here, it is equidistant. So do you get the idea? Cool? All right. This is just the converse of it. In a plane, if a point is equidistant from the endpoints, so if it says that this point is equidistant from here, then we can say that point sits on the perpendicular bisector, just the converse. Basically the other way around. All right, this last one, concurrency of perpendicular bisectors of a triangle. The perpendicular bisectors of a triangle intersect at a point that is equidistant from the vertices of the triangle. I'm going to point this out to you on the other side. Don't remind me if I forget. I should remember. But all right, turn it over. I'll explain that on the other side. So let's work with this a little bit. Perpendicular bisector theorem. In this diagram, line RS is the perpendicular bisector of PQ. Just out of good habit, I'm going to mark up what that tells me. I also know that since R is on the perpendicular bisector, what else do I know? That these are equidistant or congruent. So I'm just going to kind of write that down just for the terminology's sake. R is equidistant from P and Q. So I'm guessing you can see what we have to do first in order to find PR. What do we have to do?
Equal.
Got to find X. So we're going to set them equal to each other. And subtract 8X from both sides. And you get this. Divide by -2. And X is a decimal, and that's okay. And so then we just plug that back into, we need PR here, so we're going to plug it back in. Equals 27. So PR equals 27. Not bad, huh? Okay. Let's take a look at this. In the diagram, line JM is the perpendicular bisector of HK. Well, I'm going to kind of mark up what I see here. I already see that they made that a right angle, but then I know that that's congruent to that. I know that JH and JK are congruent. What else do I see on here that's congruent? These two, right? We could say JM is congruent to itself, but we don't really need that. That's more just for writing a proof. So which lengths in the diagram are equal? So we kind of marked that all up, so we're just going to write it down. HM is congruent to KM. JH is congruent to JK. And then we also see that LH is congruent to LK. Okay, so the next question says, is L right here on line JM?
Yeah.
It is. A line goes forever. See, it's got these little arrows here, right? And it goes forever. And the other reason I know that it's on this line is because why? Because those are congruent. Those are equidistant to the two segments joining the segment that is perpendicular bisector. Two. There's a lot of words there. So I would just write yes, because HL is congruent to KL. Or equidistant would be a better word, but that's okay. Okay, this last part has to do with that last theorem, the concurrency of perpendicular bisectors of a triangle. So first of all, I read it yesterday. I'm like, what are they talking about? And I think it's a little bit easier if we insert some words here. So it says P is equidistant from the three vertices. So here's P, and this is a vertice, and that's a vertice and vertice, right? Even though it's not marked on there, what does that tell me? P is what? Be bold, I can't hear you. Equidistant means what? Yeah, if I were to measure from here to here, it'd be the same. Okay? That's what it means. That point of concurrency there is the same distance from each of the vertices. But here's the other thing. If you write here, if, put an if there. If you're working with an acute triangle, then P, that point of concurrency, will be inside the triangle. Here, if you're working with a right triangle, then P, the point of concurrency, will be on one of the sides of the triangle. And then if you're working with an obtuse triangle, P is outside the triangle. You could, and it would still be outside though, wouldn't it? So how did they find P in each of these? Remember, how did they come up with P in each of those? What are they doing? Yeah.
Drawing a line through each segment's
Yeah, each side of the triangle, they're drawing the perpendicular bisector. And that point of concurrency is right there. Same with here, perpendicular bisector, and then up here, which is really hard to see. That's what they're working with here, point of concurrency. All right? Now, the other thing, this theorem right here, the perpendicular bisectors of a triangle intersect, we just kind of talked about that. But the other thing you're going to find out when you explore tomorrow is if you put a compass, which is your favorite thing, on the P and on one of the vertices, and then you draw a circle, it goes through all the vertices, which just kind of makes sense because of that theorem. It should kind of make sense because it's the same distance. Same with this one. It'll go through all the vertices of the triangle. Okay? So that's that. No proofs. Do you miss them?
No, never. You can't.